Robert Petersen. Controls on free subduction style based on numerical models. So this will run.
Yeah. I have another one.
Yeah, let's use yours. No, no, okay. First.
Yeah.
Yeah. There we go. It's just going to take a minute for it to.
So it's there.
Okay, so when this goes to 0, then you're cutting into your question time.
Okay. Great. Thanks, Dave. And thanks to the organizers for putting this meeting together. There's been a lot of great talks, and I've been learning a lot here. So as Dave said, I'm going to go over a little bit of work we've been doing on free subduction models and numerical simulations. This work Dave and I are doing at UC San Diego. Here's a little outline. I'm just going to go over some background very briefly, talk about also some short history maybe of Mantle convection and free subduction models so far. I'm going to highlight our setup and what we're doing there and some approaches we're taking. Run through some models, make a conclusion or an impression, and maybe talk about an interesting phenomenon. I got that the other way around. So I'm interested in Earth-like subduction. I think Paul did a great introduction on all types of subduction that we can find everywhere. But this is what Wikipedia tells me that Earth-like subduction looks like, which I guess is something that we all are sort of familiar with. We have this kind of downgoing plate and an overriding plate and some interesting phenomena up on top. And it's really this one-sided asymmetric subduction that is unique to Earth and something that's interesting. So why do we even know this is true? I like to put these in here just to remind myself. So this is just some seismic zone. Here's a profile line here of the seismicity from the Coral Islands earthquake of 2006 magnitude 8.3. So you can see there, nicely outlined this idea of having a slab going down on one side, maybe some seismicity on the bottom even. So that's one observation, piece of evidence that we can look to why we should believe this. The other one, of course, is seismic tomography, where we turn speed into temperature. And this is from Caltech. This is supposed to be a picture of the slab going under Mexico. And tomography is important because actually in Mexico, of course, famously, it's like anonymously, it's quiet there. I mean, we don't have this seismicity that we really expect. So we have to look at all these things and make ourselves believe that this is true. So that's the type of thing I want to model. I want to model something that looks like Earth. So here's a famous, just a Mantle convection sort of toy problem, and it's nice. It's bottom heated, and you get these beautiful upwellings and these downwellings that are definitely two-sided. But you get these, convective cells, and this is, I think, sort of exactly what you read in the textbook and so on about what convection looks like. So if you, first order, if you just try and make a convection model, then you're going to get something like this, and you don't get something that looks like Earth. So there's some things that we can do and things that people in the community have done in the past. You can make these sort of low viscosity weak zones here. So this is a big, low viscosity mantle wedge, something that's been applied to the model. Here's another, the same author, also between the two plates, the subducting plate and the overriding plate, you have this nice low viscosity decoupling zone. But it's, again, something that's been applied, and viscosity's been set by hand. And so wanting to make something that's self-consistent, we want to try and avoid that. And so that's some of the work that we're trying to do. So we're trying to model self-consistent Earth-like subduction. So I'm just going to talk about some of the features quickly. First of all, we use Paul's code STAGYY, and this includes the energy equation. So this is going to present some things that we have to account for. We use an Arrhenius law rheology. We have a plastic yielding that's applied. These next two things, Paul covered why we need them, but so I'm just going to only mention that we have them. Which is one is this sticky air, or this pseudo-free surface that we have on top. We also apply a weak crust. And then on the sides, we just have periodic boundary conditions on the sides of these regional models, and a zero flux bottom boundary condition. So we run Paul's codes, parallelizes nicely. We run it through the EXCEED program of the National Science Foundation on Kraken and Ranger. Kraken's up front because it has a much nicer paint job than just a bunch of racks of computers that Ranger is. So this is our initial condition. Sort of looks something like this. So this top layer right here is this sticky air that we talked about. We have this half-space cooling model that's been mentioned before. So something very young over here at a trench. We can specify how long we want this to be, for example, and how thick we want that to be. So we can build that in, and this creates a temperature gradient. And then we make this perturbation to get this the subduction kicked off. We have to give it a bit of a perturbation, a downgoing there. So this is temperature Kelvin, 300 at the top, 1600. White line there, it's supposed to be 1600, so that's sort of how we identify a plate sort of thermally. So again, we don't want to impose any type of viscosity, so we get our viscosity field from that temperature field. So what's shown here is you have a hot mantle background with a viscosity 10 to the 21, colder plate that's coming down, and it has a higher viscosity. Now this layer here is this weak layer, weak crust that we've put in on top. So that's about 2 orders of magnitude, 100 times weaker than the background mantle. And then we have a viscosity that we set for the air. We set the air viscosity to 10 to the 18, and we clip the viscosity, or we limit how low the viscosity can get for our mantle material at 10 to the 19. So our air is always at least a order of magnitude lower viscosity than our background material there. So we can add an overriding plate also just by putting in a temperature there. And then along with the sticky air at the surface, we can specify, this is a picture here of the same model setup, and it's got, these are tracers that are in the model. The red species is our air I told you about. The blue is sort of this background mantle, and this white here is this weak layer. So when we make that perturbation, we sort of put a frosting of weaker material going down. And so this is what you get. It's a little bit hard to see on the big screen. I wanted to show that actually the viscosity along that plate there is quite a bit less than it would otherwise be. So one of the big things that we have to deal with then is since we have such a we've constrained ourselves on what initial conditions we want to apply. We basically lay out some material properties. We give a temperature profile. The viscosity is then calculated based on that. And then we give it a bit of a perturbation, and we let it run. And so the thing is that when you include the energy equation that you don't get in a lot of free subduction models, this nice setup that we've worked so hard to get can change rapidly. And here's a movie a 3D movie of, this is the plate going down. So this is an isosurface here at 1600. And what happens immediately, if you remember, initially we had this background material without an overriding plate was just this mantle material at the surface. It cools off real quickly, and everything is starting to cool. And what happens is, even though there's no overriding plate, one sort of developed, and we get this nasty coupling that looks like, I don't know, a tongue sort of hanging down. It's been inflamed or something, and starts coupling with that, and we get this distinctly not Earth-like two-sided subduction. So this is something we want to avoid. And the problem is that we have this. We include the energy equation, and so we get this coupling that we want to avoid. So here's another model that's going to show, this time we actually do impose an overriding plate. There's just a small gap there of hot material, and we're going to see a movie in a sec here and watch what happens to it. It real rapidly just absolutely disappears, and you can see there just on the temperature side, all that material, that low viscosity decoupling zone disappeared on us. Here's the same film in viscosity colors, and you can see right there even more clearly how this overriding plate just comes in and couples. So that gap that we had initially there was a fairly small gap, something I almost say 25 kilometer gap. So we can actually make the gap a bit bigger, and here we've got it at a 150 kilometer spacing between the overriding plate and the downgoing plate. We've got this big area here. The idea here is to, we'll get the movie going. You want to get that corner flow going, and you see it develops nicely. And so, in fact, you still have a little bit of hot material up there between the two plates. We can show the same thing with viscosity, and you'll see now we have this clearly one-sided subduction, and even though it cooled down, since we have that sticky air, or I'm sorry, that weak crust up there, we maintain this nice decoupled zone. Go next. Okay, so the thing is that the thermal, so what we just showed is thermal diffusion is going to cause the interface between the two plates to cool. Viscosity of that material is going to increase, and you get this viscous coupling and two-sided subduction. A well-developed corner flow, like I showed you, if you spread those plates out a bit, can return this hot, low viscosity material to the interface, but only for a short time. And the reason is because diffusion always wins. And so we need to give it a source of low viscosity material, a bit of performance enhancement for our models. And so like a Tour de France cyclist, we can dope the material in the decoupled zone with extra amount of this weak crust and maintain this single-sided subduction for longer. And that's what you see here. So this sort of cyan color is this weak crust that we've thrown in there. Sorry?
I think including the temperature dependence of the thermal conductivity that might help you. That's one of the team.
Right. You could have it. Yeah. That's a good point. So what happens is as that plate goes down, you just get this really super low viscosity that's hanging there. And then what happens is as that runs out, actually, you end up just pulling the plate over, and as that material runs out, this is sort of an interesting phenomenon. You can actually then you sort of switch which side you're subducting on. So the idea being that you always need that low viscosity zone there, and if you're doing a self-consistent model, you need a self-consistent way to generate that. So one of the things this model, like I said, I doped that area there, just threw in some weak crust, so I'd always have that. But I think, as a first exploration of that, I'm going to argue that that's okay. I mean, we really believe that these crusts can be hydrated and release their volatiles, and you should not only be able to get hot material in there, but you should be able to, have this volatile release create additional low viscosity zone. So, okay, here's the conclusions or thoughts. Decoupling zone between the overriding plates is absolutely required for single-sided subduction. Thermal diffusion acts to counteract that. decoupling zone, and it has to be replenished with the low viscosity material from somewhere. So in these simple models, I just put it on top, had a source there, but I really think that you can make an argument that what happens on Earth is that you get this this hydrated plates going down and making a low viscosity sort of corner wedge there. I guess the takeaway is if you want to be self-consistent in your models, you need to really, really be self-consistent, because if you start doing stuff that the Earth wants, and I think somebody said, you try and make it simple, but you might make it too simple, because you need to actually then account for how does the Earth keep its low viscosity stuff going, and so that's something you need to account for in your models. So I just want to say thank you, first of all to Paul for inventing StagYY. It's super helpful to me, and also just a shout out to Exceed, whose supercomputers we use to run this stuff. So I think I have 2 minutes now, right? Take a good question. Yeah, hey, Margaret.
Okay, great. That was interesting talk. I have a couple comments on the sense of like imposing or trying to have more dynamic. Either it seemed how do I want to say it? So you showed the bill in Gurn's 2001 model where they impose a low viscosity mantle wedge, like work that was done like 10 years ago.
Sure.
Right? Yeah. So more recently, since work incorporating the experimentally derived flow law for olivine aggregates, like the 2007 paper that you then showed, this model, the low viscosity region dynamically emerges because of the strain rate dependence between the nonlinear dependence between the stress and the strain rate. In your models, are you having a parallel relationship? I mean, do you have that effect with the composite viscosities, or only temperature sensitive? It looks as if in your models you don't have the laterally variable viscosity emerging in the mantle wedge, nor a strong core emerging either.
Right.
That do emerge in the Dillon and Hurt. So you set this up as if there was all these constraints imposed in this model, but it actually looks as if in your model you are imposing more. You have in this case, you have that model. You have a frosting, right? And she has, in this model, there's the weak zone.
Sure.
But otherwise, in these models, you have a low viscosity that emerges in the wedge and a strong core that emerges that you don't have in yours.
Right. I mean, but absolutely. So I'm going to agree with you there, and I'm just going to go back to the point. If you want to be self-consistent, you really need to be fully self-consistent. So to the extent that I'm not, shame on me. I put that frosting down, but in the same way, I mean, that frosting is legit, because in the same way that I put that perturbation down, it's going to carry some of that weak material with it. So that element I don't see as an inconsistency, but yeah, definitely your point is well taken.
Yeah, I mean, we totally agree, which is the reason why, like the models I do, are comparable to those that we go in the Hurt, where we also impose a weak zone. It's representing this, in your case, sediments, or however, something weak along interface.
Absolutely.
But just to be clear for the audience, somewhat misrepresenting. Whereas the 2001 models, there was a low viscosity wedge imposed, but more recently they emerged, and these aren't in these models. So, there's pros and cons, but we should be fair to actually work this way.
Yeah, absolutely.
They emerge even Newtonian viscosity, though.
Not because of strain rate dependency. You don't have that parallel relation between the stress and strain rate for in diffusion creep in a Newtonian model. But you can adjust grain size in a Newtonian model in diffusion creep. You can have a parallel relation between, I mean, at least for the deformation of olivine aggregates, that work's been done. I mean, Corrado's looked at this, Greg Hurst looked at this. You have, for dislocation creep, you have,
The point is you need some weakening mechanism. It can be grain size, hydration, or something. Or power law.
Yeah.
Any kind of weakening mechanism.
But the seismic anisotropy comes from dislocation creep, and that dislocation creep is from the parallel relation. I mean, that same dislocation creep mechanism gives you the parallel relation between the stress and strain rate. So that is consistent. Using that flow law is consistent with observations of anisotropy, suggesting that, at least in this part of the mantle, that's a down and deformation mechanism.
Cool. Yeah. Yes, Connor.
You talk about self-consistency. One of the things that's interesting in looking at what happens to your model is that the slab, or the plate itself is not being regenerated at anything like the same thickness as the plate that you have starting.
That's right. Yeah.
So it's like you have an incredibly
slow,
overly buoyant plate there that can't be maintained self-consistently. So it's like there's an inconsistency between the thermal Rayleigh number of the problem itself and the buoyancy distribution that you're starting out with.
Yeah, no, I mean that's a fair point. I mean, if you were to look at something like that with those distances on the bottom, and you had a plate that, you know, I say I want a plate this thick and I want it this long, right? So there's no self-consistency there. I mean, that's a good point. I mean, what you end up with is a plate that would have moved super slowly to develop that thickness, and then, I mean, so that's the initial condition. But after that, then yeah, I mean, all the actual physics take effect. So I have to start with something.
Okay. It's coffee break.